Hello everybody, welcome. We're going to kick off in a second. We're just testing some audio. Perfect. Hello everybody and welcome to the 2022 meeting of the Four Societies. My name is Dr. Jo Lackenby and I'm the President of the Australian Nuclear Association, or ANA. It's my great pleasure to be hosting today's event, along with Dr. Mark Ho, the ANA Vice President, and Dr. John Harries, the ANA Secretary. Thanks to Dr. Harries for organising most of today's event. It's so fantastic to see everybody here in flesh today, from head to toe, not head to shoulders, as we're all used to, but you're pretty much faceless, so it's a bit strange looking at you all today. Welcome everybody who's online as well. Thank you for joining us. The ANA would like to acknowledge the Gadigal people of the Eora Nation, upon whose ancestral lands we are meeting today. We would like to pay respect to the elders, both past and present, acknowledging them as the traditional custodians of knowledge for this land. For those of you who aren't familiar with the Four Societies, Four Societies meetings, these are an annual lecture that have taken place since 1991, involving, you guessed it, four societies. So these four societies are the Australian Institute of Energy. A big shout out to the new chair of the Sydney branch, Mr. Martin Cousins. The Australian Nuclear Association, the Nuclear Engineering Panel, Sydney branch of Engineers Australia, chaired by Tony Irwin, and the Royal Society of New South Wales, whose president is Susan Pond. Thank you everyone who's here today from one of those four societies. If you are listening today, but you're not a member of any of these societies, I encourage you to go and have a look at them and consider joining if their work is of interest to you. Today we have a special guest lecture from Professor Stephen Wilson. But before I introduce Professor Wilson, a few housekeeping items. So if anybody in this room, we'd ask that you try to keep your mask on if you're not drinking or asking a question, just to minimize the spread of COVID, should anyone unfortunately have it today. After the presentation, we are going to have a live Q&A and there will be a roaming mic in this room. Please try to keep your questions succinct, just so that Stephen doesn't have to paraphrase too much for the online audience. We'll also take questions online as well. So Professor Wilson will speak for approximately 45 minutes, followed by Q&A, and we'll look to finish the lecture at about 7:30. So with no further ado, Professor Stephen Wilson is an adjunct professor at the University of Queensland. He has worked at the intersection of engineering, economics and policy, energy security, and the geopolitics of energy and resources across 3 decades and in over 30 countries. Stephen has worked on projects in energy efficiency and demand-side management, electricity regulation, tariffs, and pricing. He has also worked on climate change and energy policy, natural gas, pipeline and storage infrastructure master plans, security of supply and bankability studies, coal and uranium mining, renewable energy, and system modelling. So I think it's fair to say that Stephen knows a bit about energy and economics and how the two things come together. Originally trained as a mechanical engineer, Stephen has spent his career in energy economics, based mostly as a consultant based in Melbourne, Hong Kong, and later London, as general manager of market and industry analysis in the energy product group of a global mining company, and as a full-time teaching and research professor at the University of Queensland. I think Stephen's quite busy. One last thing, he is also managing director of Cape Otway Associates. So today, Professor Wilson will be speaking on a topic that I think is of great interest to many, if not all of us: engineering and related challenges in decarbonising the electricity system. Over to you, Professor Wilson.
Thank you, Joe, for that kind introduction. And it's a real pleasure to be here, as Joe said, in person after so many Zoom meetings that we've all been on. Distinguished guests, ladies and gentlemen, thank you to Dr. John Harries, who on behalf of the ANA extended the invitation to me to speak. And thank you to all of you for coming along to listen. While the invitation came to me from the ANA, my talk today is not about nuclear power, although I will touch briefly on that topic along the way. Let me begin with two short questions. The first question is, which is more important, your heart or your brain? You don't have to raise your hand and answer, but while that question bubbles away in the back of your mind, your pulse may quicken ever so slightly. The second question goes more directly to our topic today, and that is electricity a product or a service? Now, if your instinctive response to this question is define electricity, then I like your style. So what do we know about decarbonising electricity systems, and what do we know about the context of this challenge? The first thing that we know is that, thanks, Joe. The first thing that we know is it's a goal, and it's a simple goal. Basically, supply electricity without emitting any CO2. I think the second thing we know is that it's part of a larger goal to decarbonise energy and indeed the entire economy. So if we look, the left-hand chart here is a representation of total global greenhouse gas emissions for the whole world by sector from our World in Data. And that's represented in a certain sort of, drawn from the national accounts and represented in a certain way. The chart on the right is one I prepared for a study we did a few years ago for New South Wales. So that's the one on the left is global, the one on the right is specific to the state of New South Wales. You'll see that there's a lot of similarity between these two charts. And if you look around the world at the data, the different states of Australia and around the world, you'll see some variation, but the same general pattern will emerge. And the chart on the right shows a little more clearly where the electricity sector fits in. That's burning a lot of those fuels, starting at 12 o'clock and then working your way around to about 5 o'clock is the energy industries, much of which is the electricity sector. So the third thing I think is that decarbonising electricity is a necessary but not sufficient condition to achieve the far larger goal of net zero emissions by 2050. So you can see it's the biggest piece of the pie there, whether you're looking at New South Wales or looking at the world. It's the single largest category, but it's still only part of the energy emissions, and energy emissions in turn are only one part of all emissions. I think the fourth thing is that decarbonising electricity is actually the easiest part of decarbonising energy. And that's why it's tended to attract people as the first place to go for quite a long time now. But having said that decarbonising electricity is the easiest part of decarbonising energy, the next thing is that I think we're starting to realise that it's far from easy. It entails many difficult challenges, and that's really our topic today. So in this, there are engineering-related challenges as well as mere engineering challenges. Contrary to some popular views, there's a growing realisation that decarbonising electricity systems is more likely to be difficult, slow, and expensive than it is to be easy, quick, and cheap. And there are ways to make the challenge even harder than it needs to be if we are silly enough to do that. But wait, I hear someone ask. We put a man on the moon way back in 1969. Surely we can decarbonise electricity systems by 2050. So let's explore that thought. And to do that, I'll start by comparing the two goals. And then I do want to pause on the word we, as in we put a man on the moon. And then I'll share some examples of engineering and related challenges that I think are interesting and need to be given some more attention and more thought. And then I'll close with some suggestions on perhaps how we might reframe our thinking and our approach going forward. So let's compare the two goals. So first, the Moonshot Goal. So straight from the President's mouth, we've all heard this. And it's one of those great landmark inspirational speeches of the 20th century. It's pretty clear, those few short words in that sentence, and it was burned indelibly into individual and collective consciousness of many people. And indeed, the goal was achieved slightly inside the deadline that he set, about 5 months inside the end of the 1960s. And in duplicate, of course, both Neil Armstrong and Buzz Aldrin landed on the moon and returned safely to Earth. And then it was repeated 5 times over, up to Apollo 17 in December 1972. And only Apollo 13 was a sort of partial failure in not landing on the moon, but I think most people would agree that it was an even greater success in that they were able to return the crew safely to Earth despite the failure that they had. So let's look now at our electricity decarbonisation goal. I didn't find a speech that had been made in Canberra or London or Washington that would raise goosebumps or that is as cut and dried as JFK's 30-word sentence in his 1961 address to Congress. I did find a White House fact sheet, a recent one, didn't raise any goosebumps for me, but on the face of it, and that's taken from the fact sheet, on the face of it, the goal appears well defined. So I think we are safe in summarising the goal as supply all electricity without emitting any CO2. Now, in the US and the UK, this is to happen, according to the official government policy, by 2035. And we notice when we read the White House fact sheet that this will be a happy byproduct of good paying union jobs, quote unquote, and technology leadership. And in the UK, it is subject to security of supply concerns. And in Australia, according to current policy, it is expected to be part of the wider net zero goal by 2050. I think it's evident that unlike Kennedy's clear-cut moonshot goal, there are constraints and competing goals, ranging from the jobs and the union members' wages to industrial and regional development, technology leadership, and through to security of supply. And meanwhile, there's some scope for ambiguity on the extent to which electricity systems are expected not just to decarbonise themselves, but at the same time to grow enormously as a lever to decarbonise other sectors. So that needs to be kept in mind. It's a bit like, we need to go to the moon. Oh, and by the way, we also need to get to Mars at the same time. So I think engineers, as a result of our training, I think we will naturally worry about unreconcilable competing goals. And so I think the clarity of the goal is something that we need to have on our list of engineering and related challenges. So please don't take this as a criticism. It's just intended as a factual observation of reality. So let's think about the word we. I think this is perhaps the most overused and undefined word in discussions about the energy transition and about climate change. As we, as in we need to reduce CO2 emissions to net zero. We need to decarbonize electricity. And, you know, we put a man on the moon. Now, I do notice that neither Kennedy nor Biden nor Boris Johnson or Scott Morrison they did not use the vague word we. They were more specific. So Kennedy said this nation, Biden said the United States, Boris Johnson said the government, and Scott Morrison said the Morrison government. So it's in general public conversation. I think we hear this overuse of the word we, and I fear that many times when people say we, they really mean you. So having thought about that, let's turn now to compare the scale of resources that were required for the lunar program alongside estimates of what people think will be required for the decarbonisation program, both in absolute terms and in relative terms, so the scale of the resources. So between 1960 and 1973, a population that during that timeframe averaged about 200 million people, obviously it grew during that time, but on average was about 200 million Americans. They allocated through their government about $280 billion in today's money. It was about 28 billion in dollars of the day. Out of, in today's money, out of about $65,000 billion of GDP, $65 trillion of GDP through all those years, if you just look at the cumulative GDP through those years. So to put 12 men on the moon and return them safely to Earth. So that was a huge effort, obviously, but 280 divided by 65,000 is 0.43% of the economy. So that gives you some sense of the scale. But what about the cost of decarbonisation? Well, estimates of this vary widely and are contentious. The first thing I think we need to recognise is that we're talking about net zero emissions for every man, woman and child every year forever. So the nature of this goal, I think, is different than focusing on a small number of people on a very defined mission. The Net Zero America study estimates that the net present value of the annual energy system costs, so this is not just electricity, but the annual energy system costs from 2020 to 2030 is 26 to 28 trillion in 2018 dollars for 5 different decarbonisation cases versus 22 trillion for the reference case. So they're saying about 4 trillion incremental dollars, 4 to 6 trillion dollars incremental cost in America. And a significant chunk of that obviously will be for the electricity sector. The Princeton team that did that study estimated that at least 2.5 trillion of additional capital will need to be mobilised in this decade in any scenario. Remember, there's a lot of path dependency here with all of these things, and up to about $10 trillion of capital, additional capital, will need to be mobilised by 2050. There's another key point that it's not just the investment capital in the physical assets, but hundreds of billions of dollars of pre-FID, so pre-final investment decision capital is needed. So at least 190 billion before 2030 and at least 600 billion by 2050. So that money, that pre-FID capital that's needed to develop real physical projects in the real world, that's typically spent 1 to 5 years in advance of committing the multi-trillion-dollar investments. And remember that you can't go to the bank and borrow that money. That's all equity capital fully at risk. You know, you might go all the way through to the feasibility study and get into the room with the bankers and find that for whatever reason, you can't get the project over the line. Now at the global level, so that was for America only, those numbers. At the global level, McKinsey estimates that from 2021 to 2050, the capital cost of achieving the goals that were set out in Glasgow would amount to $275 trillion or 7.5% of cumulative global GDP. So these are big numbers. You can see that the magnitude we're talking about is much larger than for the Apollo program. And when we talk about the whole world, of course, we're not just talking about the wealthiest and most powerful country in the world. We're talking about all the countries and the rapidly growing middle-income countries and the low-income countries as well. But if your head is spinning trying to visualize all these billions and trillions we're talking about here, here's one way to think about it. So just the development work to achieve net zero by 2050, so all that pre-investment decision work, in America alone, so that's from project concepts to feasibility studies through to financing, right? All the work before the approval of the actual physical project, that's about twice the scale of the Apollo program. 600 billion by 2050. Now, albeit that would be spread over 3 decades rather than 1 decade, then there's the actual investment itself. So that's something like 20 times the pre-FID expenditure. And they're just the US numbers. And remember, the US is about, at the moment, 13.5% of global CO2 emissions, and the percentage share is falling. So that's not all for electricity, of course, but because electricity is expected to play a proportionately larger role in every decarbonisation model that I've ever seen, I think it's safe to say that capital mobilisation is one of the most significant engineering-related challenges. So I think one of the big challenges for engineers is not how can we do clever stuff expensively for middle-class people worried about the climate. It's how can we do things in a really clever way that doesn't cost a huge amount of capital, that doesn't require a huge amount of capital. The smarter we can be, the more that can be achieved with the same capital, or the less capital can be invested to achieve the same result, the more effective, the more chance we have of achieving something approximating this goal. So I'll just make 2 observations to wrap up on the comparison of these goals. So that the size difference between the Apollo program and the global decarbonisation program, it's larger than an order of magnitude, right? So this, I think, when you start talking about orders of magnitude and larger, you're not just talking about quantitative differences. You start to talk about qualitative differences between the goals. And although Australia's electricity sector is, it's quite small in global terms, the nature of the challenge that we will face here will be essentially the same in its nature. Now, the second observation I want to make is that goals are for central planners. The need for a goal at all cuts right across what I would call the received view that a market-based approach is best way to approach challenges, and including in electricity systems. So that's been the widely accepted view in Australia since the early to mid 1990s, since we did the big market reform. But obviously people remember the Hilmer Review in '93. And before that, I just came across it the other day, actually, there was a very important industry commission report, the Paul Keating Commission as Treasurer, that reported in May 1991, that was all about making recommendations about the introduction of competition to both the electricity and the gas sectors. So the consensus that was built by Paul Keating, Jeff Kennett in Victoria, other people, people in the business community, people in academia, I think was one of the most astonishing and the most broad consensus that's been achieved on a major policy question since Federation in Australia. And I'm not seeing yet that we've achieved anything like that level of broad consensus across the political spectrum and business and academia when it comes to this challenge. I think it'll be very hard to achieve big technically difficult engineering challenges without that underlying social and political consensus. So let's check where we're at. We've identified 3 engineering related challenges. 1, the need for a goal, and a clear, simple, inspiring goal. I think we can say that need is met. We've identified the daunting scale and the society-wide breadth of the goal. I think that is not widely appreciated. And I think we're starting to get a sense of the strain of contradictions with existing beliefs and market systems, at least in the West, and Australia is an example of that. So let's turn our attention to some specific examples of engineering and related challenges in electricity systems. And I want to organized these examples under 3 headings: physics, prices, and policies. These are the 3 Ps. I designed a master's course on energy markets, law and policy around this idea of the 3 Ps. And I note that in the pre-Glasgow paper that I mentioned a few moments ago, McKinsey has basically organised its thinking the same way with 3 subheadings. You see that there, and then they've got 9 requirements that they enumerate there. All 9 of those requirements involve very real challenges in electricity systems. And those challenges are conjoined by the and operator, not the or operator. So you remember that when you're dealing with an and operator, you have to multiply, you don't add, right? You multiply. So to get some sense of the degree of difficulty, insert your estimate of the probability of success in each of those requirements for the electricity sector, and then multiply the probabilities. Because if you trip and fall on one of those 9 requirements, you can't achieve the goal. This is the problem. So if you're a happy optimist, willing to ascribe 90% likelihood of success to each requirement, then 0.9, 90% to the power of 9 gives you a 39% chance of success. If you're unsure, not quite sure either way, and you sort of punt 50% on each of the 9 requirements, then to the power of 9, you're now down to a 0.2% chance of success. So you get the general idea of the nature of this challenge. Now, engineering is a significant and important part of the physical challenges. And then there are the related challenges. So remember here, we're just focusing on the electricity systems, not on the whole system, and certainly not on the entire net zero picture. And I'm going to draw on Australia for my examples. The Australian electricity system is actually a nice microcosm of the 3 Ps. All 9 of those requirements are present. So let's look at our examples. So we'll start with the physical system, then we'll look at things that relate to prices, and then we'll review the policy level. So in the physical system, so we've got issue of balance challenges that include balancing power grids, okay, and then we've got attracting investment. We've got, and the policy level, we've got trust, okay. So the needs there's a need for flexible capacity. There's the issue that all of these technical responses to this challenge involve more capital intensification. We've touched on that, and new technologies, including technologies that we've not deployed yet in Australia, things like small modular reactors. Okay, so in the physical system, I think we can summarize engineering challenges under saturation problems and system level problems. My personal expectation is that Australia will be the first country to reach renewable energy saturation. And I think we're starting to see signs and symptoms of that saturation of renewable energy already. So an example of that is the deterioration of marginal loss factors, MLFs, which you can see in these charts here. So the marginal loss factor is the loss factor that's applied to either a generator or a load that's connected onto the high voltage transmission system in the national electricity market. It basically means that if the location of your plant in a particular place in the grid causes losses to be slightly higher than they would be without the plant, then there's an adjustment factor, and so you get a little bit less revenue than what you're sending out to account for losses. It's designed to encourage people to locate plants in places where it helps reduce network losses rather than increasing network losses. And conversely, if you're a load, the multiplication factor obviously works the other way. So most plants have a factor of less than 1. I think if I understand the maths correctly, I think if you average all these factors out, if you do a weighted average of all these factors, you'll get the average energy loss factor on the grid. So it's a way of, it's intended to be a fair way of pro-rating losses across the participants on the supply and demand side of the system. So what this chart is showing is that from over the decade, from 2010-11 to 2019-20, roughly a decade, did the losses go up or down? So if the losses, if the marginal loss factor increased, that's better for you because you're getting paid more. The losses are smaller. If it decreases, it's going in the wrong direction. Okay, so you can see that most of the movement has been to go below that 45-degree line. So a degradation, a decrease in marginal loss factor. And you can see that some particular assets have deteriorated quite a lot. And you can see that, these are the conventional plants in the system, the synchronous rotating machines, the coal-fired power plants, the gas-fired power plants, the hydropower plants. And on the right is the renewable plants. Now, because most of these have been built in recent times, this is just comparing 2018-19 with 2019-20. So that's a 1-year movement in the marginal loss factor for those plants. The one that suffered the most was the solar farm at Broken Hill. And on the left side, the open cycle gas plant at Broken Hill also suffered a deterioration. So this is affecting both renewable energy plants and conventional plants. So keep in mind that according to Ohm's law, these I squared R losses in networks, so they vary as the square of the current, right? So marginal losses are higher than average losses, and losses are very high at the times when you've got maximum loading on the system. Okay, that's just the way the physics works. So this is actually the reason we have a high voltage transmission system, is that in order to transmit electricity over long distances, you need to keep the losses to a very low level. Otherwise, it just doesn't make sense. In order to keep the losses low, you need to have a small current because it's being squared, and that's what's driving the losses. In order to have a small current, you need to have high voltage. So we need to transform, we need to step up to very high voltages to send it long distances, and then we step back down, and then ultimately it comes out of our power point, right? So that's why we have an AC synchronous network. We'll come to that. So this is a problem for resources, whether it's a load or a generator that's electrically near each other, or where operating patterns are highly coincident. So if generators and loads are far apart, if they're tending to highly load the system, then they'll tend to have bad marginal loss factors. So many of the system benefits of renewable energy that are hoped for, people talk about decentralizing generation, are actually cancelled out by two effects: coincidence and co-location. So the sun's shining equally on all, it doesn't matter, you spread the solar farms all around and they're quote unquote decentralized. The sun's shining on all of them at very much the same time. Wind patterns tend to be very large, even on you have continental scale weather patterns. So there's a very high degree of coincidence in electrical engineering jargon between these kinds of generators. So that is one of the drivers of this problem. And then when you have a lot of resources piling up in the same area because, you know, it's a great, fantastic, attractive, windy location, then you're putting a lot of flows on the networks and you're tending to drive losses. So those are two effects which tend to cancel out a lot of the hoped for benefits of decentralization. So one response to this problem is to increase transmission capacity. It seems like the obvious thing to do. The difficulty with that is that when you expand transmission capacity, you reduce asset utilization, and that has a cost. You know, the same asset with lower utilization is going to need to charge higher cost. Or conversely, if you don't expand the transmission capacity, then you find yourself in a situation where you need to curtail. You may need to curtail some of this generation. And one of the trends we're seeing, it's another sign and symptom of saturation, is increasing curtailment of renewable energy generation. And so that also has a cost. So the actual levelized cost you end up with is less than you thought when you first did your calculations. So all reasonably realistic models of power systems that are looking at high to very high shares of variable renewable energy, even when storage is allowed for, will show you an optimized solution that has very high level, serious levels of curtailment. The model will tell you, yes, the optimal solution involves this big chunk of curtailment. Okay, that's a reality. Now, when you start adding these kind of resources to a system in the early years, when the shares are very low, there's almost no curtailment, might be no curtailment at all. So that's a very different picture than when you start to get to high and very high shares and you start to get more and more curtailment. So these factors tend to compound. You put these things into your business model, into your discounted cash flow analysis when you go off to see your investors and your bankers. And the MLF and the curtailment and all these things, they all start to compound. And that, I think, is a symptom of saturation. Some people say, well, that's fine. That's, the market's working. Other people say, oh, it's a problem. We've got to artificially solve that problem. We have to be careful of the law of unintended consequences with all these things. Now, a corollary of substantial curtailment is the overbuilding of capacity. And this is picked up under the availability of necessary natural resources. In those 9 requirements was one of the points there. Land is crucial to building out these resources. So this infographic, which I borrowed from our study that we just completed, is looking at this issue of footprints. Okay, and so we can see that, but basically, when you've got very diffuse and underlying primary energy resources, you need very large footprints in order to generate an equivalent amount of energy. And then on top of that, you need to think about the other issues, the overbuild and the extra capacity that we talked about. Now, I've just done a little overlay on this. What you're seeing here, you see those 8 chimneys with the 4 buildings. That's basically the visual vertical profile of the former Hazelwood Power Station in Victoria, the one that was decommissioned and demolished. And the 1 square kilometre satellite photograph underneath that is the partially demolished Hazelwood Power Station. So that's exactly 1 square kilometre you're looking at there. And then beside that, on the colour photo on the top right, is the Loy Yang B coal-fired power plant. You see above that the vertical silhouette profile of that power station, and below that, in the sort of brownish colour, is a large, similarly sized 1100 megawatt unit nuclear power plant from Sanmen in China. I've actually visited that plant when it was under construction, so you get a little bit of a sense of the visual profile and the vertical footprint. And then on the right is a footprint of a 12-unit small modular reactor plant and the profile above that. So then here on the right, we've got a couple of wind turbines. The largest wind turbine in the world, the GE Halliards there on the right. You can see the size of that relative to the Sydney Harbour Bridge or an Airbus A380s. These are quite large machines. I think Siemens have got one even slightly larger now. It's a little bit hard on this slide to show the footprint of a wind farm or a solar farm. So I've done that separately. I'll show you the solar farm example. So I was trying to find a large solar farm. This is the Western Downs solar farm, not built yet, I don't think, but it's in development. 460 megawatts. And so you can see our 1 square kilometre little square there is now much smaller than it was in our previous slide, and the 25 square kilometre area I've shown there. So this is to scale, and the map underneath is the countryside surrounding. This is taken from the publicly available environmental impact assessment. So I was looking at this and I was I wasn't quite getting a feel for how big is that? So I zoomed out. So that's the same solar farm there zoomed out. And you can now see next to it, just to the east, the Kogan Creek coal-fired power plant. That's the largest single unit on the national electricity market, a single 750 megawatt unit. And inside that red square is the power plant and the coal mine, the pit and everything, it's all there. And then you can see the town of Chinchilla to the north and Dolby down there to the southeast, and an 84-kilometre straight line between them. So I'm sort of trying to get a feel for scale. And you can see all the little dots in the lower part of this slide, all those little circles. That's the coal seam gas fields in that area. So I'm still struggling a little bit grasp this scale. So I decided, okay, what I'll do is I'll compare it with Sydney Harbour and see what does this look like if we rescale and put it on top of Sydney Harbour. So you're all familiar with Sydney Harbour. You can see the bridge there in the middle of the city. And that's what 25 square kilometres and 1 square kilometre looks like on that scale of map, thanks to Google Earth. There's the bridge and the profile of the bridge to scale looks like that. It's about 500 metres from one side to the other, tower to tower. So here's our solar farm. So what I found is that I couldn't fit it on this scale of map. So I turned it sideways. I know that's wrong. I've got north pointing to the east here, but that's how big the Western Downs solar farm is, the 460 megawatt solar farm. And if we zoom out to a higher altitude, we can see it side by side with Sydney. Now, remember from our earlier slide with all the numbers on the table, that it's giving you about 1 million megawatt hours a year at 25% capacity factor. To get the same annual energy generation that you would get from, say, about a gigawatt of conventional plant, coal or nuclear, for example, you need about 8 of these. And then if you had a bad marginal loss factor, you probably need a bit more. And if you had round trip through storage losses, you need some more. And then you have some curtailment. Even with storage, it's still economic to curtail some. So you probably end up with something like 10 or 11 or 12 of these to get the equivalent of about a gigawatt from a conventional plant that's dispatchable and has good availability. So whether you consider that this is an engineering challenge, quote unquote, or merely an engineering related challenge, I think this will bring challenges for us to do this kind of deployment at scale. So the next one is to talk about the real-time balancing problem. And the thing about electricity systems that I decided about 4 or 5 years ago that people just didn't realize. And I decided, right, I'm going to start saying this until people start screaming at me to stop because they're bored of me saying it. No one's screamed at me yet, so I'm going to say it again. The thing about power systems is you've got to balance supply and demand exactly, like sort of plus or minus 1% continuously in real time, every second of every day. It's not like milk, oh, we forgot to buy milk. Oh, and we dashed down to the supermarket and it was all gone and 7-Eleven had run out and there was none in the service station. So our family missed out on milk, but everyone else had their milk. It's not like that. You've got to balance all the supply and all the demand exactly. And if you can't do that, if it starts to get out of balance, then within about a minute, you can have the whole system collapse in a cascading blackout. The frequency will fall and then things will trip and then be overloads and it's just like a zipper coming undone. It's like you're rock climbing and you didn't get your protection in and bang, 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 it all falls out and you die, right? That's the problem with power systems. And so it's not like normal markets that you find in economic textbooks. So I think this is another saturation related problem. When you start to bring resources onto the system that make it harder and harder to do this, you've got a saturation related problem. So, I mean, you might say, oh yeah, Stephen, but you're talking about these boring, old-fashioned, silly 20th century AC power systems. We've now got these cool, groovy, everything's DC, Stephen. It's all DC now, right? That's the future. All the new generation and the storage, it's all DC, it's all inverter based. This is just a historical legacy problem. But I'm going to say, think really carefully, right? Because all the vision scenarios that you see, including the integrated system plan published by AEMO, they all entail large, long distance transmission from wind and solar farms, right? In remote areas with good resources coming into the load centers. So that means, like I said, you need high voltage to keep your I²R losses low. That means you need transformers. And if you need transformers, you need to have AC power, right? So what this means is that over a century after the current wars, a century later, Westinghouse and Tesla still win the current war. I think I'm not seeing evidence that that's changed, that we're having a sort of rediscovery of Edison's DC view of the world for power delivery. So operating large synchronous AC power grids with only DC generation, even at times, and with little or no physical inertia, rotating masses, is going to be difficult or expensive or both. When you ask, fewer and fewer of the machines that stabilize the grid to balance more and more larger and larger disturbances, that's an engineering challenge, I think. We need to have that on our list of engineering challenges, to put it mildly. So here's how we might, here's how the grid's balanced. It needs to be able to recover itself when there's a disturbance. There's little disturbances happening all the time. Okay, so, there's a disturbance, the frequency will drop. Classically, a unit trips off, you've got slightly less generation for the same load, the frequency falls, and you need to arrest that fall and then rebound and then recover. Okay. So you think about how difficult it is to balance a pencil on your fingertip. You need to make sure that the rate of change of frequency is not too steep. That's the slope of the line. That's what, if you hear electrical engineers, power system engineers talking about rock off, that's what they're talking about. And the only variable, as it happens, that affects rock off is inertia, which is the physical rotating mass in the system. I think about a spinning top. If I put a spinning top on the table, it'll just fall over. But if I spin it, it can stand up for quite a serious amount of time. Now, not indefinitely, because with energy losses, it'll gradually slow down and fall over. But in a system that's got energy behind it, you keep energizing that rotating mass and you maintain stability. Think of a beam with a pivot, and your job's to hold that steady, and there's a disturbance happening on the other end. So if you've got a nice long lever to your pivot and then a small disturbance on the end, the job's not too hard. But if I make that disturbance larger and larger, and if I move that pivot closer and closer to your hand, that job that I've given you to keep that thing steady is going to get more and more and more difficult. So that's essentially what we're doing to the system at the moment. Okay, so this is a paper that this was actually awarded one of the top 10 papers at the IEEE Power and Energy Society conference in Brisbane in December. So in this paper, Nick and Archie and I looked at the problem of frequency stability as you dial up the share of inverter-based generation, wind and solar power in the system. So this is done using a power system model, a very simple model of an idealized or stylized power system based on the swing equation. So this system had steam, hydro and wind generation, which can be taken to represent sort of all the different types of generation on the system. So here's what we found. So the first chart is looking at the system. As you go across from left to right, you're increasing the share of wind penetration. And the graph on the top left there is plotting the frequency nadir. So remember, that's that low point in the frequency following a disturbance. Where does how deep does the nadir fall after a disturbance? And you can see the points plotted across there. You can see that as you add more and more wind to the system, the depth of that disturbance before you can arrest gets deeper and deeper. And then the rate of change of frequency, what happens to the steepness of that, of the fall in frequency after a disturbance? And you can see that two things you see in the bottom here. One is that it also increases with increasing wind penetration. And secondly, that if you add fast frequency response, it makes no difference. Remember, I said the only thing that affects the rock off is the inertia. So when Nick looked at this, he said, why is it doing this? And then he looked back at the equation. He said, oh, of course, you can see in the equation that it's only inertia that affects the rock off. In the top chart, you can see that it's interesting actually, if you're below about 75%, then adding fast frequency response makes a small difference. Beyond that, it's actually making things worse, interestingly. And then on the right, the effect of synchronous condensers. If you've got no synchronous condensers, it's worse. If you add synchronous condensers, you can help relieve the problem. You can help the nadir not be quite so extreme. But notice, once you're below the yellow line, you're outside the operational tolerance, and below the red line, you're beyond what's called extreme tolerance. I mean, to recover the system from a 47 hertz event is going to be pretty difficult. I think anyone who's been in a control room probably tell you that. So the other thing I think we need to say here is that this is a sort of, if you're adding fast frequency response, if you're adding fast frequency responding batteries, if you're adding synchronous condensers, you've got this sort of one-shot response problem. And you can see that in these plots here are showing a frequency after the disturbance in the model. And you can see that the top lines sort of recover and stabilize, and then you would need to then add other generation to sort of bring the frequency back up. So it's a problem if you haven't got some primary energy you can dispatch. But the bottom two, which are at very high penetrations, 80 and 83% wind, there's a disturbance and then a recovery, and then it can't recover from a second disturbance, and it's basically going to fall over. So it's a bit like sending, if you're the general and you've got a great army and lots of soldiers and fantastic guns, and you send them out to battle, and each soldier is given one bullet. And then once he's fired his one bullet, he has to run back to the store and get another bullet and run back out to the battle again. You're not really likely to win the battle. And that's the sort of the one-shot problem with a lot of these technologies. So if the first disturbance doesn't get you, the next one probably will. So I think the implications of this work are that no existing technology can individually replace the frequency services of a synchronous generator. And when you get above about 75 to 85% inverter-based generation, I think we're going to have really serious engineering challenges. So I think there's a sort of perpetual motion machine type of problem with some of these technologies, that when you're just trying to convert flows into a high-grade energy form. So I think this is another example of the saturation challenge. I'm not alone in thinking that there's room for caution here. This is a quote from 2019. So we're nowhere near those levels of inverter-based generation or renewables in the system yet, right? But even so, people are saying, actually, we are pushing to the limit of what would be prudent. And Tapan and the guys at UQ have sort of said a similar thing. You need a certain minimum amount of inertia from synchronous generators on the system. And once you're below that, no amount of frequency control or fast frequency response from inverter-based generation can maintain your operational security. So by the way, pretty much all the batteries on the system are not doing time shifting of energy. They're providing fast frequency response, and that's great, and that helps, and they're making money in the ancillary frequency control and ancillary services markets. The big Tesla battery in South Australia is making its money like that. The 1 megawatt Tesla battery on the campus at St. Lucia at UQ is making most of its money in the fast frequency response. But that's fine for the asset owner, but if you think about the whole system problem at the sort of scale we're talking about, these are real issues. So let's just sort of just pause a moment and just do a reality check here. This is the actual physical system as it exists today. So that is a chart of the NEM showing the dispatch of the different types of plants, the brown coal at the bottom, the black coal, and then up into the gas, the orangey colors, and the wind in green, the solar in yellow, and the hydro is the blue in there. So that's basically how the system is dispatched under the market arrangements, subject to constraints in order to meet the load profile. And of course, when we look region by region to New South Wales, to Queensland, to Victoria, we see that the dominance of coal, black coal in the north and brown coal down in Victoria. South Australia is already a different story. Now, remember, these individual state or region charts are on a different scale than the main chart. You can see those little bits of orange up the top. A lot of that, not all of it, a lot of that is in South Australia. And when you look at South Australia, you can see the volatility there. So that's a tiny little fringe part of the system with a lot of volatility that's able to be balanced because it's connected with Victoria. And of course, the Victoria-Tasmania connection, that's a DC submarine connection. So that's what the system looks like. What we've been talking about is what is likely to happen if you try and turn all these other regions into something that looks a lot like South Australia. It's like it works for South Australia because it's small and Victoria's right next door and it's about 4 times as big. And then there's the Tasmania with the hydro and New South Wales and everything else that's able to help stabilise it. So I think it's important to talk about the is system, the system as it is, not just as Meredith Angler says, not the could system or the should system, but the is power system, because we have to operate this thing continuously every second of every day. So let's turn from physics to prices now. So we'll think about operation and dispatch. We'll think about costs and prices and investment. So what we're thinking about now is how those assets that constitute the physical system are operated or dispatched and how prices are formed in the market. So keep a distinction in your mind between costs and prices. We'll come to bulk, wholesale, spot energy market in a moment. But first I want to talk about the frequency control and ancillary services markets. So these are the markets that help achieve that balancing job that we've been talking about in real time. And I say markets with an S, plural, because there's many of them. So there's markets for different timeframes to raise and different timeframes to lower. So there's actually 8 of these markets all operating in parallel with the big bulk spot electricity market, what we call the gross pool in the jargon. So there's a view that some people have that these ancillary markets are they're very tiny at the moment, but they may become actually much larger, and the main bulk energy market will shrink and become smaller. So that should not be surprising that people have that view in a system that's increasingly dominated by, or people are visualizing a system with assets that have fixed costs, that are harvesting zero marginal production cost energy, that are non-dispatchable, flow-based and weather dependent. So if energy, the so-called product, costs nothing to produce, and its market value and price is converging on zero, because in competitive market conditions, you should see prices converge on costs, right? While balancing the system, including your real-time demand and everyone else's. So that's a service, right? So the product is the energy, the service is balancing the system, and the service is the S in FCAS, frequency control and ancillary services. So this might point to the answer to our question, is electricity a product or a service? And I think there's good reason to believe that FCAS markets are starting to flash some warning signs. So this chart here, which is from the Australian Energy Regulator, sorry, from AEMC reliability panel, this is showing what are called frequency excursions. So those things we were looking at in our model, what happens after a disturbance? Does the frequency maintain nice and steady, close to 50 hertz, or does it go outside the band, go into one of these excursions? Back in 2011, 12, 13, 14, 15, 16, up to about, what is that, 20, sort of 15 or so, 16, these were sort of fairly uncommon events for frequency excursions to happen. But you can see that in more recent times, there's been a really significant increase in frequency excursions on the system. And on the right, how much is that costing? You can see that there's been a trend of increasing costs for frequency control and ancillary services. So it's still only about 1%. The amount of money that's flowing through those 8 little side markets is still like 1% of the whole bulk energy pool. But people are saying this is going to get a lot bigger. The engineering question is, you know, is the market going to keep functioning? Is this going to work? So the NEM as a whole is about a $15 billion market. It used to be sort of less than 10. It went up to 20. It's about a $15 billion market. These markets are about 1% of that. So I want to focus here on, let's look at the bulk energy spot market now. So let's just focus on the South Australian corner of the market. We'll focus on that because it's like a canary in the coal mine. It's got a lot of wind and solar and capacity installed in that part of the system. The chart you're looking at here is just taking every half-hourly market price interval from August 2009 and scatter plotting in sequential order linked by a line, scatter plotting the demand, the megawatt demand on the x-axis and the price that settled on the y-axis. You can see that the weighted average price for that month was $24 a megawatt hour over a decade ago. And the average load level was just under 1,500 megawatts. Just over 1,000 gigawatt hours of energy was sent out, and the revenue pool was about $27 million. The pattern here is the classic textbook pattern of price formation as designed for electricity spot markets. We're now going to fast forward a decade. It's the same South Australian system. It's the same month of the year. It's the same method of charting the data. And you can see that the way that price formation is happening in the market, it has completely changed. It's not just that the price level changed. Most of the media and the commentary just focuses on that number in the little red box, $24 a megawatt hour, $90 a megawatt hour. But what's happening underneath those headlines is that the whole form of price formation is radically changed. So you can see the volatility. You can see that you've got a lot of high-priced events. The price can go all the way up to $15,000 a megawatt hour. It can go all the way down to negative $1,000 a megawatt hour. So this is how the market responds to volatile, non-dispatchable, weather-dependent generation. You get a completely different pattern. Let's look at the most recent August 2021. The price levels come down a little bit. We're in a pandemic, but the pattern is still basically the same. Now, if you were to look at the other months of the year, you see the same pattern. If you were to look at the other regions in the NEM, Victoria, New South Wales, Queensland, you'll see the same pattern, even though the level of renewables is not as great yet in those other parts of the market. You see the same pattern is coming, is starting to emerge. So this, South Australia is the furthest down the road. So there's a conclusion from this. What we found in our research back in mid-2017, we talked to almost all the big banks in Australia. So the big Australian banks, the American banks, the Asian banks, the European banks, anyone who would finance anything in the energy sector, the electricity sector, infrastructure. We talked to them about question related to financing. We're actually talking to them about, is it actually possible to finance a coal plant? But the discussion was, about the whole context. And all these guys said the same thing to us in their own words. And almost all of them said it to us right at the start of the interview before we even asked the question. And there was this one guy who put it really succinctly, and he said, no one can produce a bankable price forecast of the Australian electricity market today. That's what you've just seen in those charts. Okay, so it's essentially unbankable. So that one of the fundamental theories of the market is that there's a price signal, and then you can go and raise financing, and you can develop the project and build the capacity. That's not actually what's happening today in the market. So there are serious challenges. There are serious challenges from the spot market time domain, which was half hourly. Now it's every 5 minutes. Extending out to the long run investment horizon. So if we look all the way out to the long run, a decade, and out to 2050 and the end of the century, we're thinking about sustainability and the environment and security and all those things. There's real challenges there. We've seen that there are issues in the balancing side of the market, so down below the spot market from real time up to the 5-minute interval, and all these problems are rippling through. So these things are, you might not say these are strict engineering challenges, but obviously these have an impact. If you're trying to do a project, you're trying to raise capital, it's going to be relevant to an engineering project. Yeah, good. So I'm nearly there, John. So renewable energy advocates, I think, are struggling a little bit with this, but what we see very clearly in the literature is that as you dial up the share of renewable energy, the total system costs increase. So it's not just me saying this, this is a collection of papers from the international literature, from a lot of them from Europe, actually. And they see this pattern of the total system costs increase as you dial up renewable energy. So policy challenges, just to wrap up. So we've got a system with sort of modest amounts of capacity generating a lot of energy, but emitting CO2. On the other hand, resources that don't emit CO2 generating not as much energy with a lot more capacity, and we've seen the implications of that, the AC, the DC contrast. We've still got a coal-heavy system, that's just the reality of it. And that's a pattern state by state from 2006 to 2019. So there's still a very long way to go if we're to, we've hardly started to decarbonise the Australian electricity system. We've got a relatively concentrated market. That's the sort of policy setting that we're in. And, as Mr. Inoue from the Japanese ministry said back in 2014, we reviewed all energy sources and we found that no energy source is superior in every aspect. So that's basically why almost every country in the world you will find has a mix of energy sources. Big issue that we've got in Australia is retirements. We've got more than 10 gigawatts of coal plants scheduled to retire in the 2030s. And there's a lot of news about earlier retirements. There's a lot of concentration in official dates around the early 2030s, and then another 5 to 10 gigawatts in the 2040s and 50s. So by the time we get to 2050, basically almost the whole system that we see today at the generation level will be, it seems, retired. So, and that includes the gas plants. By the way, that includes all the wind turbines as well. You look at their lifespan, it includes all the solar panels, utility scale and rooftop, all those assets will reach the end of their life in this time frame. It's just the hydro that will still be there. So we're actually re-engineering a system around the hydro is one way to think of this. We don't have any nuclear in Australia, but potentially there's a potential there you could have 10 to 20 gigawatts of nuclear plants backing into that. And that we took that as the context for our nuclear study. I'd said I'd mention nuclear briefly. That's another view of the generation capacity. And then what we showed is a way that you could potentially dovetail in nuclear capacity that would resolve a lot of those issues that we've been talking about with balancing the grid and other engineering challenges. So I'll just close with that, and the quote from our Chancellor at UQs, who said on this topic, said, "We must be prepared critically to examine the various options." So I think, I'll talk more about this. I've got some copies of that study if anyone's interested. Don't want to force feed it to you, but if you're interested, feel free to take a copy. And I'll be talking more about this at the ANA conference on the 8th of April, I think here in this building. Thank you very much.